So I'm Lawrence, and thanks very much for having me here. And like Ica, I don't work on time-stepping methods, novel or not, so unfortunately you're not going to hear very much about that either. So I have a joint affiliation due to complicated things. And this is work by me, but also a cast of tens. And so my title was Specifying and Solving PDEs, and then there's an extra bit, and there's a sort of easily, and I added a question mark from the one that I sent out. So you can wonder whether or not, this is a question for you to answer. Yes? This is a question for you to think about, by the end, whether or not you think you can specify and solve PDEs easily. So I start with an introduction, because it's the beginning. So this, I think, is a sort of like, and I apologize for people at the back of the room who can't see the bottom of the slides, but I told you earlier to move forward. So a sort of barrier to progress in sort of computational science, I think, is, so this is a lemma. So developing sophisticated numerical models from scratch is quite a lot of work. I think most of us who have tried to do this would agree. And a corollary is like, if we're working on sort of new methods and so on, we might try them out on toy problems, show, oh, I get the right kind of convergence. But it takes a long time for those methods to make it from the sort of mathematical community into the applied computational science community, if they make it there at all, because people are reading the wrong kind of journals. And maybe you develop this new method, but you can only really try it out on toy problems, and it has some flaw that only exhibits itself on more complicated problems and so on. And so this is a short play in 2 acts. So a PhD student comes along, and their supervisor goes, oh, we're going to try this new thing. And they go, oh, I need to solve a PDE. And so they search on the internet, because they're a good student, and they go, well, and then they start, and they've looked for a bit, and they go, all these libraries, oh, they're far too complicated. And so then they spend about 2 weeks writing code, because they're starting out with a simple problem. And they go, oh, that was easy. And then here's Act 2. So, oh, wait, I need something else that I didn't write in the first 2 weeks. And then they spend 3 years writing code, and then they go, that was easy. And now there's another software library that people can look up and search for and find that it's too complicated or doesn't particularly address my problem. And I mean, we should be able to do better. Like, when you try and prove a new theorem, you don't start by assuming the axiom of choice and building all of mathematics on top of it. You should meet some of my friends. Let me rephrase. Were I to try and prove a new theorem, I would not. But in many ways, it seems like often in computational science, that's effectively what we do. So why might this occur? Well, here's a sort of straw man. So Mongolian is really hard, because I need to learn all these new words. And using complicated software libraries is a bit like learning a language, because there are all these new nouns and verbs I have to learn, and they don't map onto exactly what I think of. But, I mean, another way of thinking about this is like evidence that somehow that the abstraction level in these libraries is wrong, so it doesn't match the way you think about the problem. So you wrote down some maths, but now when you go to your code, you're like, well, the code doesn't look anything like the maths that I first thought of. Or maybe the abstraction level is right, but the libraries you found with this right abstraction level only work for toy problems, and you know you're going to solve something that isn't a toy problem.
Sorry, could
yeah.
it also be an occasional issue of documentation?
Yes. Yeah. It's like, I need to learn all these new words, but I don't have a dictionary. So I think that, like, if you get it right, so well-designed abstractions hopefully present a low barrier to entry, but without only being useful for toy problems. And then hopefully we can build on top of these things rather than starting from scratch every time. And this is what we sort of try and do in the Firedrake project, and many other people who build libraries for solving, numerically solving PDEs or what have you, do too. And with varying degrees of success. So here's an example. So in the beginning, imagine that I wanted to compute the action of the Laplacian on some vector using finite differences, and I might use a simple, in 2D, a simple 5-point stencil that looks like this. And before 1953, I would have written some code that looked like this to do it. Actually, I wouldn't have written exactly this code because these nouns and verbs are for a sort of an i386 processor and not a ENIAC. But the idea is that, can anyone tell me where in this matches up?
I can see -4.
Yeah, that's not one of those because I think this is just pointer offsetting. After 1953, you might have written something like this. This is definitely Fortran 77, it might be Fortran 1. And now at least you can see, oh, this thing looks like this, right? And I have some other stuff, but it's not very much other stuff. So that's good, right? Because now I don't have to learn all these nouns and verbs that are really complicated and I can't see what's going on. Now I can write something straightforward down and I can see how this matches up with the mathematics. And after all, Fortran is called the formula translation language for a reason. So the pros, so if you have a compiler, it's not tied to a particular piece of hardware. Hopefully most people would agree that it's easier to understand. And it's sort of composable in that you can write these subroutines together and glue them together and build more complicated models and so on. Of course, there are downsides. So you lost full control over the program execution, and the compiler made you a bad job of optimizing it. So, on a modern computer, was this an efficient implementation of this mathematics? Let's open it up to the room. It's a question. What do we think?
What compiler are you suggesting I use?
Whichever one you like. So I would say that on modern CPU hardware, with most compilers, you'll probably be leaving between a factor of 5 and 10 on the floor if you wrote the code like this. On the floor or on the table. Because you've got sort of caches, and you need to do cache blocking to get good performance there. This code doesn't perfectly vectorize, so you probably want to do like partial array of structure of arrays. Data transposition, so it does perfectly vectorize. And there are two problems with that. One, you didn't know you had to write the code like that. 3 problems. 2, if you do it, it's probably quite fragile to the particular hardware you optimized for. And 3, you no longer have this lovely code that looks like the mathematics. So therefore, obviously, we should just write this, right? Because now we've got full control over what's going on, and we can make sure we get perfect vectorization and everything. So the lesson somehow is like, if you can do it, you should describe what you want to happen and not implement how it's done. And I'm going to talk for most of the rest of the talk about solving PDEs using the finite element method. And I think here, with the finite element method, there's a really nice way that you can, mathematically you're describing what you're doing, but you can describe what you're doing in code without really implementing most of the time. So solving PDEs. So our finite element crash course for those in the room who don't know the finite element method. So I want to solve a PDE with some boundary conditions. You can have some other boundary conditions if you want. And I'm not going to solve it pointwise, but I'm going to seek a weak solution in some space of functions V, and then I'm going to find U in that V such that weakly I solve the equation I first thought of, so that for any test function in the space, this integral is 0. This is an infinite dimensional space. That's not good for computers most of the time. So what I'm going to do is I'm going to choose a discrete finite dimensional subspace of V and seek UH in VH. And with the finite elements, I pick the basis for VH with finite support. It's only supported on an element, basically. Divide my domain into a triangulation, my integral, because there's a sum over the elements, or the integral over the elements. I'm going to perform the element integrals with numerical quadrature. So now I can do this on a computer, because I just have to manipulate floating point numbers. And this guy here is the user-specified bit, and it sort of sits in the innermost loop. So immediately I have added complexity in the form of more code. So compared to the simple finite difference code, I need things like numerical quadrature, I probably need orthogonal polynomials. If I have unstructured meshes, I need indirections from the mesh topology to the data and all this kind of thing. And so I at least can't fit the action of the Laplacian on a slide anymore. Well, I could make it really small, but that's sort of cheating. There's another added complexity, is that the modern hardware is terrible. Or, if not terrible, it's certainly not what we want. So we have too many cores, and Eike was talking a bit about this. So if you like GPUs, depending on how you count, modern GPUs have either 56 or 3,500 cores. Xeon Phi, so these Intel accelerators, have like 72, Broadwell have 22, and all these things have fine-grained concurrency. So these 56 cores on my NVIDIA chip have a low clock rate. I don't like that for serial computation. I'd like if this clock rate were 50 rather than 1.5, and a vector width of 32 doubles. Broadwell chips, which are in sort of like Xeon servers that you buy now, have sort of up to 22 cores, sort of the same clock rate, vector width of 4 doubles. The Xeon Phi, 72, 1.5, 8 doubles. Skylake, which is the next generation Xeon, is going to look basically indistinguishable from a Xeon Phi. It's going to have half the cores, slightly higher clock rate, and same vector width. And ARM V8, there's a ARM system going in Bristol soon, if not now. I don't know who's supplying the chips. It's almost certainly going to be Cavium. They're very cagey about what the spec looks like, but the vector width is going to look something like this. So it all looks the same. So I need to be able to write code that exploits all this fine-grained concurrency and huge amounts of parallelism and runs at a really low clock rate. And doing that is sort of antithetical to writing clear, understandable code, if I write it all by hand. So what about solving PDEs again? So simple finite difference models can't be programmed from scratch. Probably you shouldn't even do that, because you don't know how to write loops properly. But no one should attempt to write a finite element model from scratch. Oh wait, some people have. So here is a very non-exhaustive alphabetized list of some finite element frameworks. German, French, Scandinavian, British, French, American, Austrian, British. I'm sure there are others. And these are varying degrees of traditional to sort of automated. So DL2 is a traditional library, Dune is a traditional library, but, and I'll come to that later, Feel++, is a combination of a sort of traditional C++ library plus some sort of syntax for automation. Phoenix is sort of automated finite element, so is Firedrake. FreeFem is sort of automated finite elements. MFem, ngsolve, and umflib are all sort of traditional libraries. Oh yeah. So I think of Nectar++ as a sort of it's a library for doing finite element computations, but I think of it more as like a code that you can plug together to solve Navier-Stokes. So NEC 5000 is another finite element code which can solve Navier-Stokes.
a general purpose library for solving an Navier-Stokes equation with a particular kind of time step.
Yeah. Exactly. So yeah, hence non-exhaustive. There's a ... here. You can think of a ... in between every one of these lines if you like, because I'm sure that you can fit one in. So the computational model for the finite elements is like, so if we go back here, so think about what I'm doing. I said, here's my element integral, now do it everywhere. And so the sort of abstract computational model is I do a gather from global to local data, I do my element integral on local data, and then I scatter from local to global data. And all these software libraries sort of provide APIs for each of these steps. And so you might end up writing code that looks like this in one of these libraries. So does anyone know what this does?
It appears to evaluate the Jacobian volume.
Yeah. So what if so not all of the things are declared because it's in a class. If I tell you that grad hat is the gradient of the basis functions in reference space. Any idea? Okay, so this computes the element tensor for the Laplacian on a single element and accumulates it into a global matrix down here. So you can see, obviously, so here's... Oh, this won't be recorded. Never mind. I'll talk louder. Where there are no pens, never mind.
Get a pen.
I can probably just talk at this. So this is grad of the basis function. This is Jacobian inverse transpose. You could read that here at least. And you, like, as any fool know, if you transform from physical to reference space through some mapping, then the gradient transforms as the inverse transpose of the Jacobian. So that's what I'm doing here. So this is the physical gradient. So physical gradient is J inverse transpose of the reference gradient. So you can see J inverse transpose hitting the reference gradient is the physical gradient. And then, well, the Poisson operator is symmetric, so it's just the physical gradient times the physical gradient into each element of the element tensor. So that was the simplest possible thing you could write down. Eike described an implementation of an anisotropic advection diffusion problem earlier, and like, it's, how many, it's like 1,500 lines of code?
Whenever I look at it, that level is that.
Okay, so maybe by now it's like, so maybe it's 3,000 by now. This is from a tutorial of one of the finite element libraries I listed on the previous page. So this is like the best possible code you could write in this library. So the pros, so it's not tied to a particular discretization. Well, it sort of is. It's tied to a discretization that's affine mapped. It's relatively easy to understand. I mean, compared to the assembly language, it's relatively easy to understand, but everyone in the room was a bit mystified. But maybe they just didn't want to say something wrong. It's sort of extensible once the code is understood, so if you want to put in like a diffusion coefficient, you sort of know where to put it, you just have to sort of whack it in here. And you're free to do what you want, so you can manually vectorize if you like. But there are downsides, because I've lost full control over the data layout and the execution. So it's like, what happened when I was evaluating this integration element at a quadrature point? The compiler may do a bad job of optimizing. Same old story. It's like Mongolian. I need to learn lots more nouns and verbs. And I may do a bad job of producing high-performance code, or maybe the library writers did a bad job of producing high-performance code. But if I think the library writers did a bad job, why am I so much smarter than everyone else? So, I mean, this is a step forward from writing everything yourself. Derek?
Yeah, I think there's another con, because when you have a language like this, I assume there's something underneath of this. I assume there's something underneath of it as well. So you also add another layer that you should be understanding if you want to do your job.
I don't know. I mean, this is just templated C++, so...
Okay, in that case. I thought it was more DSL, but if it's just templated C++, then no, the layer itself is complex enough.
So an assertion, so once we've picked the discretization for our PDE, writing the element integral is mechanical. It may be complicated, but it's mechanical. Now, computers are good at mechanical things, so why don't we get the computer to write the element integral? Seems obvious, or at least it seems like a position one could reasonably defend. And so that's sort of what we do in the Firedrake project and what Phoenix does, and what some other finite element codes do in different ways. So the idea, so here's some things that I think you ought to be able to do, because if you're trying to solve PDEs, especially if you're trying to like employ new methods or incorporate new terms into your problem, well, you don't know what the best thing is, so you want to be able to, once you've set up the model, do some experimentation. Because if it takes a long time and a lot of effort to do experimentation, you probably won't do a lot of experimentation. So here are some questions you can ask yourself, and I'll try and answer them in the context of Firedrake later in the talk. So how much do I have to do to sort of change the preconditioner I'm using for my problem? And I talked a lot about preconditioners before. Drop terms in the operator I'm using to precondition, use a different operator precondition, and run quasi-Newton rather than full Newton, use matrix-free actions, precondition matrix-free problems, and so on and so forth. And I would claim, especially in sort of like research settings, there is no prototype code. Research groups don't typically have any resources to rewrite models, so once you've written it, it stays written. And you'll just sort of hack on top of it and keep going. Also, there's a sort of psychological aspect here in that like we're all really precious about the code we write. We don't like throwing it away. Sometimes, I don't know. And so ideally you'd love to have efficient code first time round. On the other hand, do you have the expertise to do this?
Yeah, there's another one that I can think of, perhaps this one. Mm-hmm. But also, the larger your code, usually the more difficult it is to modify.
Yes, yes. So if you have lots of code, it's hard to modify it. Yeah. So all of the rest of the stuff in this talk is in the context of Firedrake, which is an automated finite element system. We have a logo. We've got a website. There's a paper. It's now appeared, so you can update your BibTeX file. It appeared in the last month of December 2016, whereas it was on the archive in the first month of 2015, so the review process was speedy. And it has a development team that is mostly based at Imperial. So there's Thomas Gibson, who's a PhD student of Colin and David. There's David. There's Miklos, who is a PhD student of mostly David, but really himself. There's me. There's Fabio, who was a PhD student with David and Paul, and now works for Jared Gorman in Earth Sciences, doing I'm not quite sure what. And TJ is a new PhD student of Paul. Baylor, Rob Kirby, who's also been heavily involved in the Phoenix project. So this is Robert C. Kirby, not the R. Mike Kirby, who works on finite element methods at Utah with Spencer Sherwin. At Bath, Andrew McRae, who used to be a PhD student of Colin and David, slightly grayed out. At ECMWF, Florian Rathgeber. And at IBM, there's Doru, that's how that's pronounced, Berseya. And there are people actually using this to solve problems. So there are people like Colin and Gemma using it at Imperial. There are people like Andrew and maybe Jack, I don't know, some of the time, at Bath using it. Onno Bokova's group at Leeds. I don't know if you have people looking.
Not yet.
Not yet. There's a group doing...
From Firedrake import star.
There's a group doing optimal control at Kiel. Matt Nepley, who's one of the PETSI developers, once he realized that students aren't Matt Nepley, has got his students using Firedrake to solve finite element problems and preconditioning. University of Houston, we had someone doing sort of subsurface flow. At Oregon Health and Science, we've got someone building a coastal ocean model. Some people at Exeter, I think, are maybe looking at it. There's someone doing like early stage bone growth at ETH. The University of Waterloo, Francis Poulin is doing things with quasi-geostrophy. Jeffrey Dillon at Minnesota and Rob Kirby at Baylor. So it's sort of like, it's a sort of, in some sense, a real software product in that hopefully you can pick it off the shelf and use it to some extent. And we have documentation and tutorials that are maybe useful even. Firedrake, so the title of this paper, which I didn't put in, is Firedrake, automating the finite element method by composing abstractions. And so a lot of the game we play is to try and find the overarching sort of mathematical or computational idea in the thing we're trying to do, and then ruthlessly write less and less code until like the abstraction is right and we can do nice things. So we build on and extend embedded domain-specific languages developed in the Phoenix project. Here's a website. In particular, the unified form language, there's a paper in Tom's, which is used to specify the variational forms. And then a symbolic problem description, which is generic, is sort of woven together with problem-specific data executed by a runtime Python library. This is Firedrake that does JIT code compilation and so on. So the idea is that few of us like to do this, which is skiing uphill, looking at our feet, working really hard. I mean, to be fair, if they turned around and looked at the view, it would be beautiful. Instead, we prefer to do this, which is, as sort of users of computational models, we like skiing downhill because it's easy and fun and we can see the view and so on. This is a photo from Visit Norway, and this is a photo from a ski mountaineering race somewhere in Switzerland. This is also, in some sense, the approach we take sort of in the project itself, in that what we try and do is we try and synthesize solutions from symbolic problem descriptions, because synthesis is easy, that's running downhill, whereas analysis is hard. Anyone who's had anything to do with compilers knows that analysis is really hard. But synthesis is really easy. Synthesis is, you can think about, if I've got a load of cake ingredients and I mix them together, I get a cake batter. Analysis is taking the cake batter and unmixing them into the ingredients, and then remixing them into a different cake batter. So the descriptive approach, so, okay, I showed some code before for computing the element tensor for a Poisson problem, and the idea with domain-specific languages is you make things like that easier to do in that you pick a natural language for expressing things that fits the problem domain. So here is how I would do this in Firedrake and Phoenix. So hopefully, if you're vaguely familiar with the finite element method and vector calculus, you can read this and see what's going on. And so the symbolic description, so it's an implementation of the maths, not the numerics. And so hopefully, if I'm just trying to solve PDEs, I can concentrate on the numerical aspects and not the low-level code. On the other hand, I don't control everything. In fact, I control very little as an end user, but did I need to? A compiler turns this into something that looks like this. I elided a little bit of code. But it basically does the same thing the code snippet I showed before does, just sort of unrolled because this isn't really designed for human consumption. Okay, so here is another slide with some questions on it so you can think about and maybe try and answer. So hardware-aware optimization of finite element kernels is a job for one, more, or none of these people. What do we think? So I think probably it's not a numerical analyst. It's probably not a geodynamicist who just wants to like solve some fluid problems or something, or a computational chemist if they're doing computational chemistry. Maybe it's a computational scientist, maybe it's a computer scientist, maybe it's a combination of these last two people somehow. Yeah?
I would say none of them.
Okay.
The vendor should do it.
My vendor should do it.
Yeah, I mean, finite element kernels are so incredibly common. It's in every vendor's interest to have fast executing codes.
Okay, so this is where I think you're asking your vendor to unmix your cake batter for you, which is hard. And I think, and it's basically, I mean, you might say, oh, what I should do is I should ask, like, my generic compiler should be able to optimize these kernels. And that is the computational scientist equivalent of saying machine learning is the answer to everything.
I think there's a problem with that. HPC, unfortunately, is a pretty small share of most vendors' revenues.
Yeah, okay, but I guess with hardware, where I thought you meant really the particular processor architecture. I wasn't talking about parallelization.
So nothing to do with parallelization.
Yeah.
The thing is that if I give you some low-level C code, then the analysis that I have to do to determine that there are things like loop invariants that I can pull out, unrolled matrix vector products that I can hand off to a fast BLAS library and so on, is too complicated. What you're asking for is compiler authors are not magicians, nor are they 1,000 times smarter than you are. If you have information at the point where you're synthesizing the code, then you can make a much smarter implementation job than a compiler that has to analyze low-level code to determine that information that you already knew.
Yeah, I guess the reason why I was wondering about this is because I had the impression that finite element kernels also used a lot outside of science, so that's why I thought
I mean, my experience is no, and I think what you see is the kind of transformations that you need to do to get good performance are not the kind of things that you easily, that unless you're specifically looking for, you would necessarily find. So how do we do this? So this mathematical description is the thing that says, this is what I want to do on each element. And this is a variational form, and we use a domain compiler, which is, for obvious reasons, called a form compiler, that turns this into low-level code. And there are various ones available. So the Dune folk, mostly led by Stefan Muting, who Eike mentioned in the previous talk, never wanting to write the code that he wrote for the advection diffusion problem by hand again, are looking at using UFL to run through a form compiler that's specially designed to do some factorization and so on, to get low-level code that runs well. The Phoenix project has for a long time had a form compiler called the Phoenix form compiler, and the Firedrake project has a form compiler called the two-stage form compiler, which Miklos has been writing, and it's called two stages because it has two stages in it. And if I have a compiler, the natural thing to ask is well, can I use it as an optimizing compiler? So the code snippets I showed you are both, this one isn't independent of polynomial degree, but changing the polynomial degree means changing this number, so it's sort of independent because the form compiler does the work for you. The other one is independent of polynomial degree, but the naive implementation I showed is algorithmically suboptimal, very suboptimal, so Eike was saying about sum factorization. So it reduces operation count for evaluating residuals from order p to the 2d, so in 3d that's p to the 6, to dp to the d plus 1, which in 3d is 3 times p to the 4. So if p is 7, which is something that many people want, then this is 7 to the 6, which is a large number, and this is 3 times 7 to the 4, which is a large but smaller number. So, can I do this? Well, I have a high-level description. I know what transformations I need to apply and where they need to apply them. Oh yeah, so for any computer scientists in the room, sum factorization is just loop invariant code motion. So, I can do this. So on a hexahedron, I think actually if you write this in Firedrake, this won't work, but never mind. Yeah, I spelled it out well. At degree 7, the naive implementation of the residual evaluation needs on a single cell nearly 7 million floating point operations, whereas the sum factored implementation needs 185,000. So, can you write this by hand? Of course you can. Do you want to write it by hand? I would claim no. Moreover, not everyone has the expertise to do this by hand, and by providing automated systems, we can sort of scale out the optimization and expertise. So the in-person case-by-case optimization does not scale because, oh, I need to change the problem, I need to add some new terms, oh, I've got to spend 3 months optimizing my operator evaluation. The code generation allows us to package expertise and provide it to everyone. So if you pull down Firedrake and use it, you can get access to sort of fast sum-factored algorithms. They're at least algorithmically optimal, if not sort of constant factor optimal. And it's done by this domain compiler. And anecdotally, research groups that had implemented high-performance finite element code by hand are now turning to domain compilers, because they want to solve different problems and they don't want to invest 6 months getting the finite element kernels working fast by hand. It's a point where, like, if you only have to do it once, it's okay, I can pay a postdoc to do it for 6 months. If I have to do it 10 times, well, I can't afford to pay a postdoc to do it for 60 months. If you're a big research group in Germany. Yeah. Okay, so all I showed was toy models. Well, complex models you should also be able to do, and so here's a comparatively complex model, and the aim is that all your code should always be able to fit on a single slide. So here are the equations for sort of Bernard convection with the Boussinesq approximation, and I'm using Taylor-Hood finite elements, and I can just about fit it on a slide if I allied some things to do with the boundary conditions. And hopefully you can see, well, here's the specification of the problem, really, and like you can hopefully see, so this is in strong form, and this is in weak form, but hopefully you can see what's going on. And then I can solve this with Newton, and the thing with having a symbolic thing is I wrote down this residual, and I can differentiate it symbolically to get the Jacobian, the linearizations, the Jacobian. So I don't have to do them both. If my problem comes from minimizing some energy functional, I can write down the functional, differentiate that to get the residual, differentiate that to get the Jacobian. And so I can do the thing that I would have done in the maths rather than doing everything in the maths. Working all the maths out on paper, working out the implementation on paper, and then sort of transcribing the implementation. And it is more than a pretty face, so The high-level language enables, hopefully, rapid model development and ease of experimentation, and you don't have to write much code if you're trying to solve problems. From our point of view, well, we can automate complex optimizations, so if someone else picks up our code, we don't have this problem that, and like someone who uses Firedrake goes along and says, oh, you should use this new finite element software, it's great. And they pick it up and they code up their model and it runs really slowly. I mean, sometimes that does happen, but that's their fault, not our fault. Definitely all the time. And they go, but they go to their mate, oh, it runs really slowly. And so their mate goes, oh, what you need to do is you need to email Lawrence and you sit down with him for 6 months and he works through and he types out all the things and then it runs really fast. And I'm not really even willing to do that once.
Well, I'm sure your fees are very competitive.
Yeah. So the idea is that like we can sort of automate the optimizations, and so therefore you get the equivalent of like the high skill domain programmer sitting down with you for 6 months to get like your optimized model. So we can exploit expertise across different disciplines. So the Fabio, who's a computer scientist and compiler person who worked in the group, doesn't really know about the finite element method at all, but
I don't think he knows what that funny upside triangle thing was.
I think just about does now. But like he doesn't have to, because at the point at which he starts, what he sees is basically tensor algebra and loop structure that he needs to optimize. And we have a small library code base because the abstractions are right and we have a generative approach. So fast prototyping is good, but I have to rewrite for performance, is a mantra you often hear. It's like, oh, I'll try it out in MATLAB and then when it's working, I'll rewrite it in C++. We think that's not necessary. So Firedrake provides computational performance that's often within 50% of achievable peak in some metrics, and there are some papers where we show this.
For hero, substitute James Madison.
Yeah. So hero coding is, so James's codes don't run that fast. No. Hero coding is necessary if you want the last 10, 20, 30%, but what is the person cost, particularly? It's maintainable, so core Firedrake code is about 22,000 lines of code. And we share some components with Phoenix, and that's about another 17,000. But for a complex, like, compared to other big software codes, so I don't know, so DL2, I think, is about 600,000 lines of code. Dune is, it's hard to count because you don't know where to look, but like hundreds of thousands probably. Okay, they're sort of doing more things, like they have more components built in that we've outsourced to other libraries, but I'm happy that I only have to maintain 22,000 lines of code. You can build models fast, so in the context of coastal ocean, Thomas Kerner, who is at the Oregon Health and Science University, is the lead developer of Thetis, which has a website. It's a 3D unstructured coastal ocean model, well, 2 plus 1D unstructured coastal ocean model in Firedrake. It's about 6,500 lines of code, and depending on the problem, it's between 4 or 8 times faster than the previous code in the group that uses the same numerics. So, is that previous code fast? Well, it's not as fast as the current as this new one, but it was obviously fast enough that they didn't want to spend more effort optimizing it or decided they couldn't. Similarly, so Colin and Gemma work on Gusto, which has a website, and it's a 3D atmospheric dynamical core using implementing the Met Office gung-ho numerics. And I counted, it's 1,600 lines of code, which isn't very much.
It's not because we're lazy.
Yeah. Yeah, so I think a really bad metric for how much, for efficiency of programmer is like how many lines of code per day you write. I think it should be more how many kinds of lines of code per day you delete. Well, are we done? Okay, and so finally, so I could talk a lot about solving implicit systems. I'm going to talk about solving implicit systems too a bit, but from a slightly different perspective. So I can write down a residual. Great. That's nice if all I want to do is explicit time stepping, but most of the time I don't just want to do explicit time stepping. So I want to do implicit time stepping, so I need to solve an implicit system. So it's easy to write those down, but the challenge is usually in solving them. We hook up to PETC, which is the Portable Extensible Tools Kit for Solver Composition. Actually, no, it's the Portable Extensible Toolkit for Scientific Computation, but you can use the alternate acronym if you want, for solving linear and nonlinear systems of equations. And so you can get any algebraic solver you like, plus composition of block elimination field split solvers. So this is sort of things like algebraic multigrid, direct solvers, splitting methods for factorizations, and so on. And the field split stuff I'll come to. So here's the first sort of controversial statement in the talk. I think we really need to get away from thinking about the idea that, like, what solver are you using? GMRes. What solver are you using? BiCG-STAB. What solver are you using? CG. Krylov methods are not solvers. We should think instead that Krylov methods mop up the modes that our preconditioner doesn't handle perfectly. So, what solver are you using? Algebraic multigrid, and I'm fixing things up with CG because it's not perfect. So, when you design your next lecture course on iterative methods, you can start with this and then talk about Krylov solvers. And one of the things with that statement is that, well, coupled problems make this really hard because coupled problems are typically not amenable to black box solution methods over and above LU factorization. And LU factorization doesn't work if I'm in 3D and I want to solve large problems in a finite amount of time. And for large problems, we often use these approximate block factorizations. And there are many, many configuration options, and they may require problem-specific auxiliary operators, lumping, all of the things, and so on. And sort of after the work I did with Iker, well, mostly Iker did, where he wrote all of this stuff for this multigrid solver, sort of by hand and so on. Last summer, when Rob Kirby was on sabbatical here, we sort of thought about, what is it that's going on? Can we sort of capture the abstraction here in such a way that makes it easier to write complicated solvers that maybe need auxiliary operators and so on? So basically, sort of algebraic linear solver libraries are good when what you need to, when all the preconditioners you want can be constructed algebraically. If I just give you a matrix, I can do things to the matrix to get the preconditioner. But lots of things don't get that. So, block preconditioning. So, leaving aside monolithic, which is sometimes better but harder to implement, state-of-the-art preconditioning for multivariate problems is typically based on block LU factorizations. Why? So the rationale for that is that if I take this matrix, which may be a saddle point, but like D cannot be 0, and I precondition it with this operator, which is diagonal, then this has minimal polynomial of degree 4, and thus a Krylov method converges in at most 4 iterations. If I do these inverses exactly. So there's a short note from 2000 from Murphy, Gene Golub, and Andy Wathan that sort of points this out, and then Ibsen in 2001 treats the case of D not equal to 0. The minimal polynomial comes out the same. Or function space preconditioning. So if you're interested in like iterative solvers, I can very much recommend this book, which is a short Siam Spotlight book. These two papers are very nice as well. So these only use block diagonal operators, and sometime, so here's an example, so if you do time-dependent Stokes with an implicit time-stepping method, you get an operator, a boundary value problem at each time step that looks like this that you need to solve. And it turns out you can precondition that, having done some functional analysis, with a block diagonal operator that looks like this. So this top block is nice and easy because it's just the inverse of that, and that's a nice Helmholtz problem, so I can hit that with algebraic multigrid. This is the sum of the inverse of two operators. So I can't write down a matrix and invert that. So what I need to do is I need to invert the identity, or in finite element, the mass matrix onto it, and then additively compose that with the inverse of the Laplacian. So you can see that, for example, this thing I can't do algebraically by manipulating the discretization of this matrix. And so here's my Rayleigh-Bernard convection again, and so when I do Newton linearization, I get a Jacobian that has this kind of block structure, and so I have the Navier-Stokes operator here, a scalar convection diffusion problem here, and some asymmetric coupling. And so we'll invert J with a Krylov method, and so we need a preconditioner. So let's write N for the Navier-Stokes block, and M1 tilde and M2 tilde for these two coupling terms, and block eliminate N in J, and we get a system for the temperature, which is a Schur complement thing, which is the convection diffusion plus this. And in 2012, Vicky Howell and Rob Kirby showed that K inverse is a good preconditioner for ST, at least in infinite dimensional spaces, because if you hit that, you see that this becomes the identity, and this thing becomes a compact perturbation, and Krylov methods converge superlinearly on compact perturbations of the identity. So the Newton update, so I need to solve that, and if I write some notation, if I write Kj, bold J to denote approximating J inverse using an iteration K on J using J as a preconditioner, then this iteration empirically converges swiftly and only requires inverses or preconditioners for N and K. So Navier-Stokes, so here's a paper on fast iterative solvers for and finite elements in the context of fluid dynamics, talking a lot about Schur complement factorizations and block eliminations. And a lower Schur complement factorization of N is a good option. And so I need the inverse of SP, where this is grad, and that's div, and this is the inverse of the vector convection diffusion operator, so that's dense, so I don't want to form that. And lots of these approximations come about by making arguments about approximate commutators. And so this is the pressure convection diffusion approximation, where I approximate the inverse of S by the inverse of a mass matrix, the action of a scalar convection diffusion operator, and then the inverse of a stiffness matrix. And so our recipe for inverting Navier-Stokes is this horrible expression here. So things to know, I only never need inverses of diagonal blocks. I can apply operators matrix free. The inverses are nested, and we need ways of controlling the inner iterations. And all these auxiliary discretized operators don't appear in the original system matrix, so I need some way of feeding them into the solver. But of course, I have a finite element library that knows how to discretize and assemble all these auxiliary operators. So I just need to make a way, I need to figure out a way of making the sort of like the communication between the PDE library and the solver library bidirectional rather than unidirectional. So obviously there's an answer to this, otherwise I wouldn't be talking about it so enthusiastically. So a combination of Firedrake, which I've been talking about, and PETSI to the rescue. So we already have with PETSI highly configurable, runtime configurable library for algebraically composing solvers. And I can build these auxiliary operators easily, and so we just combine those two things, just. So we have 2 new bits, a matrix type that implements matrix-free actions and remembers the discretization, the sort of symbolic discretization that it came from, and custom preconditioners. So obviously, I can't apply ILU to a matrix for which I can only compute the action, except by applying the action to each basis vector in turn, forming the full matrix, and then doing ILU on that, but that sounds stupid. So instead, we create sort of custom preconditioners that can inspect the bilinear form and do the appropriate thing. So a very simple thing we can do is say, oh, to precondition this thing, what you should do is you should just assemble the operator and hand it off to a preconditioner for an assembled operator. So PCD, I can fit on a slide pretty much if I elide some boilerplate. So here's the pressure mass matrix, here's the pressure stiffness matrix, here's the scalar convection diffusion operator around the current state, and then I just apply the thing. How do I configure things? Well, Pepsi, if for those of you who've come into contact with it, provides a very verbose programming language for configuring objects at runtime with 2 operations: value assignment and string concatenation. So every object has an options prefix which controls where it looks for options and values. And this is very, very verbose, and if you're typing them out, it's quite tedious, but it's quite a powerful idea, and so we can control the types of individual solves by ensuring they have different prefixes, which is going to be important because if I want to solve this problem, I need to control a lot of different solves. So here's 1, 2, 3, 4, 5, 6, 7. And if I'm applying SP, there's another one down here. And so this is sort of these are all quite deeply nested in my solver, and I can write code that sort of applies this to this specific problem. But what if I now want to couple this with something else and solve a 4x4 system? Now I have to rewrite the code to incorporate that extra thing. Whereas by sort of having this sort of pluggable runtime system where you just define the preconditioners for the different block and configure them at runtime, then you can plug in your Navier-Stokes solve wherever you need it and put it together with other bits. So when I said verbose, I wasn't joking. So here's an example of let's configure the Navier-Stokes solve, which looks like that. So I'll run gmres, and I'll do a lower Schur complement factorization. So preconditioner type field split type Schur, field split Schur fact type lower. Okay, I'll approximate the inverse K here, that probably should have been F, by assembling the matrix and running a single V cycle of algebraic multigrid on it. This guy, the Schur complement, I'll again approximate just by applying the preconditioner. And that's this sort of custom thing that we wrote. I can specify whether I want an assembled matrix or not for this thing, and the preconditioner for that, and so on. And I get reasonable performance from this, and so I can solve Rayleigh-Bernard on 6,000 cores with 185,000 degrees of freedom in a constant number of Newton iterations and a basically constant number of Krylov iterations. Great. And if I stand in front of this column, so you can't read it, then this slide looks much better. And I think the problem here is that the inner solves are performing worse at larger scale because my algebraic multigrid is not optimal. But if I can plug in a better inverse for those blocks, I don't have to wind back and rewrite all of the rest of the code around it, and so So we've got this sort of runtime composability, which is good if you're playing around, because you can write the model, debug it at small scale on your laptop using LU, and then when you need to go to a big system, you can sort of scale up and put in a scalable preconditioner. And we can tune the implicit solve for Navier-Stokes on its own and then just drop it in wherever such a block needs inverted. The model formulation doesn't care about variable splitting, so I didn't have to say up front, I'm going to split the temperature away from the velocity and pressure. Obviously composes with nonlinear solvers, and if I or someone else does something in Firedrake to make residual evaluation or matrix assembly or something go faster, then I just get that for free rather than having to sort of rewrite my code to take advantage of it. I never needed to worry about parallel, so I didn't write any parallel code, or at least I didn't write any explicitly parallel code. An easy extensibility, so this is a model for phase separation in polymers. It's a bit like Cahn-Hilliard, but the energy functional is different. And a Newton iteration at each time step solves a problem that looks like this. And you can precondition it using Schur complement techniques. And here they didn't use, to determine the approximate Schur complement, they didn't use approximate commutators. They used a matching strategy where you replace the inverse of a sum of matrices with the product of inverses. S hat is this. This is a thing I need to invert, but this guy doesn't appear anywhere here. So I can't make it algebraically. Oh, it doesn't matter. I can write my preconditioner on a slide and just put it in and hit go. So sort of wrapping up, which I hope is about the right kind of time frame. Answering some questions. So once, for us at least, how much code do I have to change? To change the preconditioner between sort of 1 and 10 lines of code. So hopefully it's easy to experiment. You shouldn't experiment blindly. You should sort of like want to know where you're wanting to look. Changing the operator, well, that's easy. Similarly, different operator, quasi-Newton. The matrix-free actions is sort of one line, so I can basically flip between assembled operators and matrix-free by changing one solver configuration parameter that says whether or not I want an assembled matrix or a matrix-free matrix. And then preconditioning these matrix-free problems, well, it's more work because often you might have to write something by hand, but if what you're going to do is go to sort of like block eliminations and do algebraic things on sub-blocks, then it's not too much. If you want to do something really complicated, it's more work, and I'm working on ideas for that, but I don't have an answer yet. So summing up, so Firedrake, which might be useful for your problems, is high performance for many problems in both, I think, important metrics of programmer and computer time. It's quite a good choice for experimenting with new algorithms as long as the discretization you want is a finite element discretization, because you can run on your laptop and scale up relatively easily. I can't solve your math problems for you. However, I hope I can give you some tools that will allow you to get to the solution faster and more easily once you've solved your math problems. Obviously, you can't do everything you might want to do in the framework. We do give you some mechanisms for escaping the walled garden if you want to step only slightly away from pure finite elements. But it's not the right place to start if you want to simulate molecular dynamics. It may well not be the right place to start right now, at least if you want like NURBS and IGA. If you want to do lots of like hacky things at low level by hand, it may be not the right place to start. However, you probably shouldn't start from nowhere. And I have some questions for people. So if we're thinking about developing novel methods, how should we compare them? So what is fair? Is it iterations? Is it how accurate they are? Is it time to solution? Is it time to error? I haven't said anything about time stepping at all. One of the things here is that I think that, at least in terms of like the way we're trying to think about building software libraries, I don't know of any clean mathematical abstraction that captures a large enough class of methods. So, if you're interested in that, I'm happy to talk about it, but I don't know what the right thing to do. So some formulations, e.g. space-time DG, are quite amenable because it's just finite elements, but no one's really done the work. But on the other hand, what about sort of complex multi-level time steppers? Because you need to think about how you would compose what you're doing at each time step with sort of how you're doing the spatial discretization, and I don't think anyone's thought hard about that. And then, yeah, I've just got some references, so I'll leave these open challenges up, and with that, I'm done.